Okay, for today's lesson, we're going to take a look at the dot product of two vectors and what that means. Okay, so for the definition of a dot product, there's a little diagram here on the side that demonstrates it. And what we're doing with the dot product is we're taking and we're multiplying two scalars together. And what we're multiplying is the magnitude of A, which is going in this direction here, and then the horizontal component of B, which is this part in here. Okay, and so if we remember, how do we find that part? If we take a look again at our right triangle here, because we're looking at B is in this direction here, but we just want the horizontal component. So if we take a look at how to find that horizontal component, remember theta is, we can set this up as cos of theta is equal to the horizontal component, which is my adjacent side, what we have there. So we'll call that x for right now, over the magnitude of b, which is my hypotenuse on that triangle. Okay, so we can take that way. And then if we just rearrange that, then our x is equal to our, what we were looking for, which was the magnitude of b, cos of theta. Okay, so that's our horizontal component, and we'll see how we can apply this formula in a bit in the next few lessons as we move along with it and just get used to how it works and what the parts are of the formula. Okay, so we have the little equation above which says that A with the dot product of B. Okay, so again, when we're doing this, we're not looking at multiplication of vectors. We're looking at the dot product of the two, and we have the two components, the magnitude of my vector A and the horizontal component of my vector B. Okay, and the two vectors together, and we get a dot product between the two. Now remember, this all equals a scalar of some kind. Okay, so it'll give us a value which is just a scalar. So you can't take the dot product of three vectors, because A dotted with B dotted with C is equal to now a scalar dotted with a vector, which is impossible. Okay, so we can't do that. Okay, so moving on to the next few examples here, just to get used to how it works. So again, keeping in mind, if theta is 60, remember u and v, then these two vectors that we're talking about, wherever they are, whatever they look like, okay, the angle is in here. It's always tail to tail when we look at the angles of two vectors. So the 60 degrees would be in there. Okay, and then if we move on with, they want us to determine u dotted with v, so we would take our values here. So u, hold on, so u dotted with v is equal to, again, the magnitude of u. Okay, and then how much of v, so v would be up here and u would be down here, how much of v, the horizontal part of it, is being kind of applied to u. And in this case we have cos of 60. Okay, so our two values, magnitude of u is 5 times 10 times a half, so we get 7.5 units, and just units. Okay, so again, a scalar is what we're getting from here. Okay, just a scalar. Okay, so moving on to the next example here. So cos, now we have an angle of 120 degrees. Okay, and when we look at 120 degrees, it's actually something like this now between the two vectors. Okay, and if we think about again the projection between these two, so if you have U here and V here, okay, it's really being projected in, or if we think of how much of the horizontal component, it's going this way now with the right angle triangle that we have. So when we work this out, we'll see what we get. So U dotted with V again is magnitude of U, magnitude of V, cos of 120. Okay, and when we get this E dotted V, we're going to get a negative 25 when we work that out. Okay, so when we put in the 5, the 10 for those values, okay, so we can see now that if U dotted with V is greater than 0, we'll have an acute angle. Okay, and if U dotted with V is less than 0, we have an obtuse angle. Okay, and we can think of it as how much of that horizontal component is on V or on U from V, then it's got to be behind it. So it's going to be a negative value for that, okay? So there's the obtuse and the acute angles and what those mean, okay, in terms of the signs of the scalar that we get. Okay, for 90 degrees, there's a big, also something that happens here. And again, if we think of how we broke it down before, well, if I look at this, if U is going to be there, and if they're 90 degrees to one another, well, how much of a horizontal component of U is on V? Well, U doesn't have any horizontal component, it's just going vertically. But it also works algebraically as well. So if we break it down into U dotted with V again, magnitude of U and magnitude of V, cos of 90, okay? And we do 5 now times 10 times 0 degrees, or 0 that we get from the cos of 90 degrees, and we get 0. And again, it's looking at how much of the horizontal component is being put onto the other vector, of whichever way it's set up. But then now, if we have this, well, there isn't any, therefore, if U dotted with V is equal to 0, the vectors are perpendicular. Okay, and that's a big one. You'll see that one over and over again. Okay, and it's important when we get these perpendicular vectors. Okay, so here you have two non-zero vectors, A and B are perpendicular if and only if A dot B, take this out, that shouldn't be 90, it should be 0. Okay, so we'll get a scalar of 0 from there. If A and B are perpendicular, another term or another word you may see for perpendicular, and you will see this later, so I may as well introduce it now. So you'll see the term, if I can get my marker to work. Okay, so normal is another word that you'll see for that. Okay, so these properties here, we just need to remember them. So if we do the commutative property, so A dot B is the same, A dot B is the same as B dot A, or for any scalar, K, A, if we multiply A by the scalar and then take the dot product, or we take the dot product multiplied by the scalar, or we multiply B by the scalar and then take the dot product, those will always be the same. Okay, the distributive property, A dotted with B plus C, so we're adding two vectors together, which gives us another vector, and then we can take the dot product, or we can take the dot product and distribute through, and then add the two scalars together that we get, and we'll get the same thing. Okay, so again, remember this is two vectors. Dot product gives us a scalar in the end. This way here we have scalar plus a scalar, and it'll give us both a scalar as our final answer. Okay. So the only one we're going to take a look at in terms of knowing the steps and how to get it, how to derive it. So A dotted with A is the magnitude of A squared. So again, if we think of two vectors on their own, you have a vector. There's A, and then we put A on top of A as well. So there's A as well. They're both on top of each other. Okay, the angle theta, the angle between the two is actually 0 degrees. Okay, so if we look at now A dot A and we take our formula, well, that's the magnitude of A times the magnitude of A cos of 0 degrees. And cos of 0 is equal to 1, so we get A magnitude of A times the magnitude of A times 1, which gives us the magnitude of A all squared. Okay, and that's what we wanted. And we'll get the scalar of that, and it's just the magnitude squared. Okay, so we'll see some examples on how to apply that as well.